Hello and welcome to Lecture 2 of Wireless Data Networks Unit. The focus of this lecture is on Media Access Control or MAC. Media Access Control is a sublayer of data link layer in OSI model. To explain the communication in networks, we are using layered model. There are two main layered model, OSI model and TCP/IP model. But why we are using layered model? The first reason is it helps us to design protocols. When protocols are created for each layer, information and interfaces are defined only for that layer. Products from different vendors can work on the same network, and technology and capability changes in one layer won't affect the other layers. Also, the layered model creates a common language to describe network functions and capability. Okay, as mentioned, there are two main models, the two main layered model, OSI model and TCP/IP model. TCP/IP is a protocol model that matches the TCP/IP protocol suite. It describes the functions happening at each layer, and sometimes it is used as a reference model, but it is more protocol model. OSI model is a reference model and consistent between all network protocols and services. OSI model describes what needs to be done in each layer and not how it should be done. The TCP/IP layers are mostly known by their names, and OSI model layers are known by the number. For example, for the network layer is always referred to as layer 3. In these lectures, we are more interested on the first two layers of OSI model, which are physical layer and data link layer. Data link layer has two sublayers. The top sublayer is logical link control or LLC that operates on IEEE 802.2 standards, and it's mostly LAN technologies. This upper sublayer communicates with the network layer, and it places information in the frame that identifies which network layer protocol is being used for the frame. This information helps multiple layer 3 protocols such as IPv4 or IPv6 utilize the same network interface and media. The Media Access Control or MAC is the interest for this lecture, and it provides data link layer addressing and access to various network technologies and communicates with the physical layer. The physical layer is going to be discussed in the future lectures, and it's basically the media, the connection between in the network. So we are going to look at the different media access control techniques for wireless network in this lecture. But before we start on that, we are going to talk about the media access control techniques in general for the network and explain which one is working for the wireless and why some of them are not suitable for wireless network. But before we start on the MAC layer and techniques that's used for wireless communication, we need to know that what are the MAC services and what's the function of the medium access control layer. On transmission, it assembles data into a frame with address and error detection fields, and on reception, it disassembles the frame and performs the address recognition and error detection. It basically governs access to the LAN transmission medium. Before we start on MAC technologies, it is important to understand how data traveling between the different nodes on different network topologies. We have three main topology in the network, and the other topologies available are sort of mix of these ones. The first one is bus topology. While transmitted data is moving through stations, each station makes a copy of the data until it reaches the end of the bus that terminating resistance absorbs the data. In the ring topology, data transmitted from one station goes around the ring while each station is making a copy of it until it arrives at the sending station when it gets removed from the ring. In the star topology, when the stations are connected to a central devices such as hub, switch or repeater, this central device is responsible to transmit data to their destination. If switch is used, it selects where to send the data. Otherwise, all station receives the data. If you're using hub, for example, because hub is not making decision. So basically, the central device is sort of passing on the data. If it's a switch, it makes a decision. If it's a hub and other devices, it's just passed it on through all the other nodes. In the computer network, the medium are multi-accessed by network devices, and there is a need to use a protocol for effective media sharing method. At any given time, only one node can send and receive, otherwise collision will happen. Problem is on how to do this. Basically, who is next? The purpose of MAC techniques are to help with this problem, basically solving this problem by deciding on where and how nodes can control the medium. Whether the control type is centralized or distributed, we can decide on where each node can control the system, and how to control depends on the topology and the trade-off between the cost, performance and complexity. In centralized system or centralized model, master node deals with granting the access to the nodes for using the medium. The master node uses the polling system for granting access to each node. However, it can add overhead and reduce the amount of throughput by doing that. And the problem here is the single point of failure. So if the master node fails, the whole system is not working. And throughout the time that it is happening, the one node is taking control of the whole medium. But it is more simple and easy to install compared to distributed method. Some of the examples are token ring FDDI. Then in the distributed type, all the nodes on the system are controlling the access to the medium dynamically as well. It is more reliable than centralized approach, but it's a bit harder to implement. There are two types of distributed MAC: synchronous, when nodes are given fixed resources to transmit, and asynchronous. Resources are allocated based on the request. There are a number of MAC techniques used to help devices sharing the medium. The broad categories goes to dynamic and static approaches in MAC techniques. The dynamic MAC techniques are further classified as random or contention-based access and scheduling access. In the random access, there is no centralized node to control the access, and each node tries to gain access when it has the data to send. This method is suitable for bursty traffic with light to moderate load, and it's a simple technique to implement. Examples are Aloha and CSMA techniques. The scheduling approach gives each node a turn to send the data. The node can either decline it if it doesn't have any data, or it can start sending the data if it has the data. When the transmission is finished, the turn goes to the next node based on the predetermined logic sequence. The right to send can be controlled in centralized or distributed manner in scheduling system. Polling and token passing are examples of this approach. Scheduling is good when majority of the nodes have data to send. The static one is, there is only one method or one type of a static MAC technique, and it's called channelization. In this method, frequency, time, and space division is used for granting access to the nodes. This method is suitable for cellular network. Now we explain each technique with more detail, starting with the dynamic approach and random or contention-based access. The first one is Aloha. The name Aloha comes from the fact that this method first used in packet radio in Hawaii. In this method, when a station has a frame, it transmits the data. A station listens to known approximate time, which is the maximum round trip plus a small increment, for acknowledgement, and if the data received with no error. If no acknowledgement is received, the station starts retransmitting again. And if there is no acknowledgement even after the retransmission, the station gives up. Receiver check the frame sequence. If frame OK and address is matching, it sends the acknowledgement. Frame may be damaged by noise or other station transmitting at the same time, which is called collision. Since there is a high chance of other station transmitting at the same time, the collision is very likely to happen in this method. Any overlap of frame can cause the collision, so it doesn't matter if the frames are only 20% overlapped or 100% overlap. Still a collision happens. That's why Aloha only have the maximum of 18% utilization. The other method that created after Aloha was a slotted Aloha, when the time frame adds to the system. The time is divided in slots equal to frame transmission time, and it's all managed by central clock or other synchronization mechanism. Transmission begins at the slot boundaries, so senders only can send during those time slots. Nodes start sending data in a specific time slot, so the one that is specified at the beginning by the by the clocking system. So frames are either missed or totally overlapped. In this system, we have only 100% or zero overlap. The slotted Aloha has the maximum of 37% utilization. So you can see that the efficiency with Aloha is quite low. Even with 37% utilization for a slotted Aloha, we are still experiencing a very poor efficiency, which attributes to the fact that a node starts transmission without paying any attention to what other nodes are doing. So to avoid that, it would be good if we could just sense the medium and see what other nodes are doing, if they're transmitting or not. So if the channel is busy, we stop and then send again. This observation is the base of a contention-based technique that's called Carrier Sense Multiple Access, or CSMA. In this approach, a node having data to transmit first listens to the medium to check whether another transmission is in progress or not. The node starts sending only if the channel is free. That is where there is no carrier, basically. This technique is also known as listen before talk. There are three variations of this method: one persistent CSMA, non-persistent CSMA, and p-persistent CSMA that we are going to explain in the next slides. The propagation delay is smaller compared to the transmission time of the packet in this method. Propagation delay is the time that it takes for the bit to travel in the network, so from sender to receiver, and the transmission time is when the whole data is transmitted. All nodes immediately know that transmission has started because they are sensing the carrier. Node with data to transmit listen, as we mentioned before, to see if the medium is free, then they can send. And if it's busy, they wait. And if the two nodes still, that can happen if the two nodes are transmitting at the same time, the collision can happen. The this one is one persistent CSMA. In this case, node having data to send starts sending if the channel is sends free. So if it's free, if it's idle, the node starts transmitting. If the medium is busy, the node continues to monitor until the channel is idle and then start transmitting. It avoids the idle channel time, but the problem is that if the two stations are both waiting for the transmission, since they're both going to sense the free or idle channel, they're going to send at the same time and collision can happen. The other method is non-persistent CSMA, in which if the channel is free, the node starts sending the data. Otherwise, if the medium is busy, it waits amount of time drawn from the probability distribution, which is called basically a random time, and then it sends. The random delay reduces the probability of collisions, obviously, because it's random, but the random number in each node can be different. That's why if the two nodes are sensing the channel, they wait for different amount of time, so the collision can be avoided. But it's going to waste the capacity, because when the two nodes are sensing the busy channel, they're both going to wait for a random number, and during that time there is no transmission. The last method is p-persistent CSMA, which basically combines the other two methods and try to get the better results and utilization. In this method, if the medium is idle, the station or node transmit with the probability p and delay one time unit with probability 1 minus p. If the medium is busy, listen until idle and then step 1 starts. If the transmission is delayed because of the channel being busy, it delays it for one time unit and then step 1 happens again. In this method, the collision is reduced and the idle time as well, so the capacity can be used in a better way. To compare whatever we learned so far with Aloha and CSMA methods, we have this graph. The X is a load and the Y is a throughput. You can see the Aloha and pure Aloha has a very low utilization or very low efficiency, and slotted Aloha is a bit better but still low. When the throughput is high, it goes down. And non-persistence or p-persistence have a better results. Depending on the p value on the p-persistence, we can get the best value out of it. To make CSMA more efficient and increase the utilization, the cost of the collision should be reduced by reducing the waiting time. That's why two methods or modification added to the CSMA techniques. One is collision detection, the other one is collision avoidance. In CSMA CD, or carrier sense multiple access with collision detection, which is more popular in wired network and mostly uses the one persistent mode, it detects the collision and immediately terminates the transmission. By doing that, it avoids the waste of time continuing transmission by sender, and they retransmit the last data again after the collision. So a step goes as first step: if the medium is idle, it transmits. If the medium is busy, listen for idle, then transmit. And if the collision detected, jam signals stop the transmission. And after the jam, wait a random time, then start from step 1 again. The carrier sense multiple access with collision avoidance, or CSMA-CA, aim to prevent the collision before it happens, because in the wireless communication we are not able to detect the collision efficiently and on time. It uses a p-persistent mode of the CSMA, and it starts with sensing the medium. If it's clear, it sends the data. If the medium is busy, node waits for random time, then check the medium again. This random time is called the backoff factor, and it is managed by the counter, central counter or backoff counter. If medium is clear after the backoff reaches number 0, data will be transmitted, but if the backoff reaches 0 and the medium is not still clear, the backoff factor is going to be set again.